Hey, this is Avi Gutman with another Ask Me Anything event brought to you by quantreasoning.com. I invite you to join me live next time. We do this every Saturday at 11 a.m. Eastern, and you can attend for free by starting your free trial at quantreasoning.com. So before we solve this question itself, I want to make sure that we all really understand least common multiple. Let's imagine, just for the sake of discussing this, let's imagine we're looking for the least common multiple of 12 and 15. Okay? The first thing that I would do is find the prime boxes of 12 and 15. So 12 would be 2 squared, 3 to the 1, and 15 would be 3 to the 1, 5 to the 1. These are the prime boxes. Now here's what I want us to imagine. Let's imagine that we own a store, let's say a clothes store, and we like to keep our inventory as low as possible. Let's say that we only order inventory when we know that there's a customer coming in and we know what that customer is going to want. So our inventory is essentially always 0. Now I want you to imagine that we carry jackets that have different sizes. And the possible sizes of jackets are the prime numbers. So we have jacket size 2, 3, 5, 7, 11, 13, 17, 19, etc. Those are the types of jackets that we carry normally. And the little exponent on top of each of the primes in these prime boxes, so the 2 here and the 1 here and so on, that's how many of that type of jacket we're talking about. So if you had 5 to the power of 12, that means we have 12 jackets size 5. Okay, so the exponent tells us how many of that particular jacket, and the prime number tells us which size jacket. Okay? So with the least common multiple, the analogy would be that I have a VIP customer coming today. And because that customer is a VIP, a very important person, even though I don't know exactly what he's going to want, I want to make sure that I have it. I want to make sure that I have whichever jackets that customer will want, but I don't know ahead of time. Normally I would know ahead of time and I would just order the jackets that I know that customer will need. In this case, it's a very important customer. He hasn't decided yet. He said, I'm either going to want 2 jackets size 2 and 1 jacket size 3, or maybe I'm going to want 1 jacket size 3 and 1 jacket size 5. I don't know what I'm going to want. And so the question for me as the store owner is, what inventory do I need to have? I still want to keep it minimal. That goes with the word least from least common multiple. Least. I want to keep it as little as possible. But I need to make sure that I'm going to be able to satisfy the customer whether he chooses to go with the 2 jacket size 2 and 1 jacket size 3, or whether he chooses to go with the 1 jacket size 3 and 1 jacket size 5. He's not going to want both of the options. He's going to want one of them, but I don't know which one. So what inventory would I have to make sure that I have before the customer shows up? I'm going to need to make sure that I have 2 jackets size 2, 1 jacket size 3, because he's only going to want 1 jacket size 3 regardless of which option he goes with, and also 1 jacket size 5 just in case he goes with the second option. So that, my friends, is the least common multiple of 12 and 15. And if you multiply it out, you get 60. Right? 2 times 2 times 3 times 5 is 60, and that's the least common multiple of 12 and 15. And if we think about least common multiple in this way, then I think we have a chance of solving this data sufficiency problem without using pen and paper, or with very minimal pen and paper. So I'd like to give you all maybe another minute to think about the problem in the context of what I just described and see if you can figure it out. So I really think that the the key to our success on this problem is to really take a lot of time to think about the question stem. We're looking for the least common multiple of 12, which we know everything we need to know about 12, and x, of which we know nothing. So back to my analogy, we have a VIP customer who's going to come, and we know one of the possible options that the customer might be interested in. It's 2 squared times 3 to the 1. But we know absolutely nothing about the other option. And so, of course, we're going to need some more information in order to be able to properly prepare for the customer. But remember, we don't want to have any more inventory than we absolutely need. Again, going back to the word least and least common multiple, we want to keep it as minimal as possible. So what I would be thinking about before I even go to the statements is probably something like this. Look, if x has within its prime box up to 2 squared and up to 3 to the power of 1, that's not really very interesting because I'm going to have 2 squared and 3 to the 1 prepared for this customer anyway, because that customer might be interested in the 12, in the 2 squared 3 to the 1. So if x has any of those within it, that's not very interesting. I don't really care if it does or doesn't have up to 2 2s and 1 3. If it has more than 2 2s, or if it has more than 1 3, well, that's going to be very interesting. That's critical to know. But as long as someone tells me, look, there's no more than 2 2s, or there's no more than 1 3 in the prime box of x, then I don't actually care to know whether it does or doesn't have those 2 2s and that 1 3. It's irrelevant. Further, I'm thinking, if x does have anything beyond 2 2s and 1 3, I'm going to need to know precisely what that is. Otherwise, I can't prepare for the customer. So, to recap, what do we need to know about x in order to answer this question? We need to know whether or not it has anything more than 2 2s and 1 3. And if it does, then we need to know precisely what that is and how many of that there is. So I don't know that I would prefer to start with one statement over the other. The statements seem kind of similar in this case. So I'll just start with statement 1, just because it's the first one. And the first statement tells us that the least common multiple of x and 9 is 45. So let's think about what that tells me about x. One thing is for sure, x definitely has a 5 in it. Because if it didn't have a 5 in it, then the least common multiple of x and 9 wouldn't be 45. So the thinking that I'm doing there, you know, the prime box of 9 is this, and the prime box of 45 is this. Oh, you can't see that. There. So for x to, we introduce x, and that's causing the least common multiple to include a 5 in it. That must mean that x has a 5 in it. Is there anything else that x must have in it based on statement 1? No. Is there anything else that x could have in it based on statement 1?
3.
It could have up to 2 3s.
It could have either 1 3 or 2.
That's right. Or none. Or none. So x could have either no 3s at all, or a single 3, or 2 3s. So we don't know how many 3s there are in x. Could be 0, 1, or 2. But we do know for sure x has a 5 in it. Now let's recall what our question was. Our question was, does x have anything more than 2 2s and a single 3? And if so, what is it? What does x have beyond those? And if we are saying here that x definitely has a 5, okay, I'm fine with that part. But we're saying x could have either 0 3s, 1 3, or 2 3s, then I can't answer the original question, because does x have 2 3s or doesn't it? Those are going to lead to different answers. Because 2 3s is more than what we said we wouldn't care about. Right? We said we wouldn't care as long as it has up to 2 2s and a single 3, but if it can have more than a single 3, then I need to know. I need to know that. And statement 1 doesn't enable me to know that. Statement 1 leaves me in an uncertain place. Does it have fewer than 2 3s, or does it have 2 3s? Those will lead to different answers. So statement 1 is not sufficient on its own. We can go ahead and eliminate the answer choices that claim that it is sufficient on its own. All I care about is to show that it could have more than 1 3. Like the difference between sufficiency and insufficiency in this context is, can X have more than a single 3? Because if I know for sure X doesn't have more than a single 3, I should also mention the 2 2s. So if I know for sure X doesn't have more than 2 2s and it doesn't have more than 1 3, then we're good. Then it's sufficient. But if it may or may not have more than 1 3, if it may or may not have more than 2 2s, then it's not sufficient. So I'm not really thinking about all the possible options, although I think I did verbally state them here, but I don't really need to think about all of that. All I need to think about is, if X allows for more than a single 3, then it's not sufficient, because I don't know if it has more than a single 3 or not. So I'm really focused on, what do I know that X has, or what do I know X could have, in the context of 2 squared 3 to the power of 1. If it could have more than any of those, then it's not sufficient.
So you're not focused on the 5 or maybe the 7 or whatever the X could have been. You're only focused on what's already given through the 12.
Yeah, because with the 5 there's no uncertainty. Like as long as I know that X has a 5 in it, then I can prepare for the customer. The problem with statement 1 is I don't know whether X has 2 3s in it or not. Because if it does have 2 3s in it, I'm going to need to get another jacket size 3 just in case the customer decides to get X. But if X has fewer than 2 3s, then I don't need to get 2 jacket size 3. 1 would be enough. Whether he goes for the 12 or for the X, either way, 1 jacket size 3 will be enough. But if X could have 2 3s in it, well, now I don't know. Do I need to get 1 jacket size 3 or 2 jackets size 3? I can't decide. Yeah, let me see if I can help you with that. So going back to the original question, we stated the following. If X contains more than 2 2s and more than 1 3, and this includes other primes as well, like if it has anything other than 2 2s and 1 3, I'm going to need to know precisely what that stuff is. So whether it's other primes or whether it's more 2s or more 3s, whatever it is, I need to know precisely what that is. There can't be any uncertainty. Now with regards to the 5, there isn't any uncertainty. We know for sure from statement 1 that statement 1 has a 5 in it, that X has a 5 in it. Where we do have some uncertainty, by the way, we don't have any uncertainty about the 2s either. Statement 1 informs me that X doesn't have any 2s. So there's no uncertainty there. The only place with uncertainty for X with statement 1 is, does it have no 3s, 1 3, or 2 3s? If it was just 0 or 1, I'd be fine, because I'm going to need a 3 anyway for the 12. But if it has more than a single 3, well, that would change the amount of inventory that I need to prepare. What about statement 2? So statement 2 tells us what about X? I think it also tells us X has a 5 in it. For sure, X has a 5 in it based on statement 2. And X may or may not have up to 2 2s. It may or may not. I don't know. It might have no 2s at all. Maybe it has a single 2, maybe it has 2 2s. But we were going to prepare 2 jackets size 2 anyway. In case the VIP customer wanted the 12, we were going to have 2 jackets size 2. So do we actually need to know, in terms of our inventory management, do we need to know whether X has no 2s, a single 2, or 2 2s? But if we know that it maxes out at 2 2s, then we don't actually need to know how many 2s there are in X, because we were going to prepare 2 jacket size 2 anyway for the 12. So statement 2 is sufficient on its own because with statement 2 we know exactly what inventory to prepare for this customer. We're going to need a single jacket size 5, a single jacket size 3, and 2 jackets size 2. Do you agree with me that if we have a deep enough understanding of least common multiple, then we don't necessarily need to use a lot of pen and paper for this question? We certainly don't need to test any specific cases. I mean, if I am going to need other size jackets, then I will want to know about it. I'll want to know that I need them, and I'll want to know how many of them I need. But each of the statement on its own implies that I will need a single jacket size 5, so there's no uncertainty there. I think really the key word here, JD, is uncertainty versus certainty. There's no uncertainty about the other prime in this case. The uncertainty with statement 1 is, will we need more than the single jacket size 3 that we were going to prepare anyway? Or will that single jacket size 3 be enough in terms of that size jacket? So the answer was B. Statement 2 is sufficient on its own because it tells us everything we need to know. It tells us that we'll need a single jacket size 5, a single jacket size 3, and 2 jacket size 2. Statement 1, on the other hand, only tells us we'll need a single jacket size 5, 2 jacket size 2, and either a single jacket size 3 or 2 jackets size 3. And that either or piece is the reason why statement 1 is not sufficient on its own. I don't know how many jackets size 3 to prepare for the customer with statement 1. It's either 1 or 2. I don't know which is which, or which is the right one. And I really think the key there was to rephrase the question, as you said, JD. It's about knowing enough about X to be able to get the appropriate inventory for the possible desires of this very important customer without having to get any extra inventory more than is necessary, keeping it minimal. Hey, I'm just going to interrupt my own video for a moment here. If you're finding value in this video, please let me know in the comments below and give this video a thumbs up. It really motivates me to keep uploading a new video every day. Alright, back to the video. You both did a good job noticing that if we're talking about profit, then we need to be talking about $2 profit for P and $3.50 profit for Q. So then I would draw a number line, and I would say, look, on the low end, if all of the units were P, I'd be making $2 per unit for 834 units, which I believe is 1668. I just doubled the number 834. So that's if we're only selling P. In the other extreme, if we're only selling Q, now I have to multiply 834 times 3.5. So I would just go 800 times 3.5 is 2800. And 34 times 3.5 is just over 100. So I'm just going to approximate here because we shouldn't need to have exact numbers in data sufficiency. I'm just going to say it's approximately 1920. Excuse me, 2920. Approximately. And then I ask myself, well, where does 2000 fall on this number line? Closer to which side? And I'd say, well, it's going to be closer to the left, because if I put 2000 here, what do we have? We have like 332 in that gap. on that side versus like 920, almost 3 times as far on this side. So I could rephrase the question to, did we sell around 3 times as much of P as we did of Q? And since the question is asking, is it more than 2,000? I'm going to rephrase it further and ask, did we sell less than 3 times as much P as Q? Because the more of Q we sold, the closer we'll go to Q side, to the right. And the question is asking, are we to the right of 2,000? So did we sell, is more than a quarter of our product coming from Q? That's essentially what they're asking. Now, when I look at the statements, I'm going to say the following. Look, if we sold more units of P than of Q, that means that we're to the left of the midpoint. So if the midpoint is here, we are somewhere to the left of that, but we wanted to know which side of 2,000 we're on. Am I to the right of 2,000 or am I not to the right of 2,000? I don't know. So eliminate AD. The second statement, I would ask myself, well, where would we be on this number line if exactly 100 units of Q were sold? If exactly 100 units of Q were sold, that means 734 units of P were sold. So we'd be way closer to P than we are to Q. We'd be probably somewhere like here. Like 7 times closer to P than we are to Q, approximately. But they're telling us that it's not exactly 100 units of Q, it's at least 100 units of Q. So if as you go more and more towards Q, you're going to the right from that arrow. And again, we wanted to know which side of 2,000 we were on, left side or right side. I don't know. Eliminate B. Now the best part of this diagram is when we combine the statements, because what do we know? We know that we're to the left of the midpoint from statement 1. We know we're to the right of this arrow from statement 2. So we're somewhere in this cloud in here. But you can see visually, I still don't know which side of 2,000 I'm on, and therefore the correct answer is E. Can we make any interesting inferences at the end of the first sentence? $70 per appliance on average. Did anyone pause to make that inference when you first read the question? So I don't know at that point whether it'll be useful or not, but I think it's important, just in terms of good habits on the GMAT, it's important to at least note to myself that I could calculate the average if I wanted to. And if the math itself is very easy for me to do, then I might as well just do it. If the numbers didn't work out nicely, then I wouldn't do it, but I would still make a mental note that I could do it if I wanted to. Especially in the context, like at the top of the screen, what do we see here? We know the price per mixer, we know the price per blender, we know the price per food processor, so the average price per appliance must be somewhere within that range. Must be somewhere in between 30 and 120. And so we can start applying some logic there and do a sanity check and see, wait a minute, $70 per appliance on average, does that even make sense? Yes, it does make sense. It is somewhere in that range. So I'm just talking here about good habits when reading a word problem on the GMAT. What do you all think about taking a nice long pause at the comma? Good idea or bad idea? It's a very good idea. What could you do during that pause? Is there another inference to be made once we know the ratio of food processors to mixers? We're told that it's 2 to 1. So 2, 1 ratio units. It means that if we ignore the blenders just for a moment and imagine that we only sold food processors and mixers, and we know that we sold twice as many food processors as we did mixers, what can we infer?
Food processor and mixer, the average price is 135.
135 doesn't really make sense to me as the average price because it's not somewhere in between 30 and 120.
It would be twice as close to 120 as 30, right?
40 numbers of food processor is been sold and 20 numbers of mixer has been sold. Because total is 60.
Well, we don't know about the blenders though, so I can't say how many food processors were sold, and I can't say how many mixers were sold. All I can say is that there are twice as many food processors as mixers, which means, just as Eric said, that the average price, if we're ignoring blenders for a moment, just looking at food processors and mixers, the average price must be twice as close to 120 as it is to 30. So if we were to draw a number line with 120 on one side and 30 on the other side, we'd say that the average is twice as close to 120. So if we call that 2x, that would be x. It's twice as close to 120 as it is to 30. Where does that put us on the number line?
90.
90. That's right. We have a total of 3x representing a total of 90. That's 90. If 3x is 90, then x is 30. So we're 30 to the left of 120, which is 90. That's the big inference that, in my opinion, we must make at the comma. We must. Otherwise, we're just making our lives a lot harder than they need to be. The analogy that comes to mind is if you have 5 puzzles that you need to solve, and each puzzle has 20 pieces. What would you rather? Would you rather I take the 100 pieces of the 5 puzzles and dump them all in the desk in front of you and say good luck? Or would you rather I just dump the 20 pieces of puzzle number 1 on the desk, wait for you to complete it, and then dump the next 20 pieces of puzzle number 2, wait for you to complete that, and so on? Like, I think that's a much easier way to live your life in general, and certainly on the GMAT. Solve one problem at a time. So if we pause at the comma and we infer that the average price per appliance, excluding the blenders, is $90, and remember the first inference we made was the total overall average was $70, and we know that each blender is $50, well, isn't that so interesting that the $70 overall average is exactly halfway between 50 and 90? What does that tell you? Exactly, the total number of blenders has to exactly match the total number of mixers and food processors combined. Because the overall average for all 60 appliances is exactly halfway between the price per blender and the average price per mixer/food processor. 70 is exactly in the center between 50 and 90 on the number line. Now we could at this point say, hey, there's a total of 60 appliances, so it must be 30 blenders and a total of 30 for the mixers and food processors, and then go from there. Or a shortcut, if you say, look, I don't really need to know exactly how many appliances there are, because this is just a ratio question. We're just asking for a ratio. What was the ratio? I don't need to know how many appliances there were. I can just say, look, if I have 1 ratio unit here and 2 ratio units here, then there must be 3 ratio units here, because it's supposed to be the same number of blenders as there are mixers and food processors combined. So 2 plus 1 is 3. And then to answer the question, we want blenders to food processors. So that's 3 to 2. It's A. And I really think that each puzzle on its own is not rocket science, but what makes this question hard is you've got 4 puzzles combined, but you have to do them one at a time, I think. And then it makes it a lot easier. Is there any point in this word problem in which you think we would benefit from pausing a long pause to make some kind of big inference? And if so, where is that point? Yeah, I think probably that period after 1020 is the place to do it, although you might even want to take a pause just before the word was and say the following. 1/3 of the tickets, knowing that there are 600 tickets, is 200 tickets. And if 200 tickets were sold at $1.80, I'll just show you how I would do the math there. I would use the 2 zeros to move the decimal point 2 spaces to the right, like that. And I get 2 times 180, which is 360. So I think I would make that inference before the word was. So $360 came in from those first 200 tickets. Then I would read on to the period and say, well, that leaves me with another, what's the difference between 360 and 1020? I think the difference is 660. So 660 came from 400 tickets whose prices are $1.20 and $2.40. That's, I think, the big inference that we want to make at the period before we keep reading. And I wonder if there's any more work that we might want to do before we keep reading. I mean, we've already made some great inferences, but what else can we do here? Now that we know that we had 400 tickets at prices of either 120 or 240, I guess we could think about the range of possibilities. Like, how much money can you make if you're selling 400 tickets for those two prices? If all of the tickets were $1.20, how much money would you have made from 400 tickets at $1.20 each? I think it works out to $4.80. And $2.40 is exactly double, so what's double of $4.80? $9.60. So here's $4.80 and here's $9.60. And we know that we are at $6.60, which is closer to which side? Yeah, it's only 180 away from here, but it's 300 away from here. So I can already tell you, I can already make the inference that we must have sold more of the cheaper tickets, more of the $1.20 than of the 240. How do I know that? Because 660 is closer to 480 than it is to 960. But how much closer? What's the ratio of those distances? We've got 180 and we've got 300. Why don't we divide both by 60? Just to reduce the ratio. So 180 divided by 60 is 3. 300 divided by 60 is 5. So we've got a ratio of 5 to 3. I'll do it over here. I've got a ratio of 5 to 3 for a total of 8. And we said that who was winning? The cheaper ones. The cheaper ones was winning. So $1.20 versus 240 versus total. Look how many inferences I'm making, and I haven't even finished reading the question yet. I'm still at that period after the 1020. Now, I know what the total is. How many tickets are there total? There's 400. I had that right here, 400 tickets. So if the 8 ratio units represents 400 actual tickets, that means that my ratio has a scale factor of 50. So I can infer now either of these by multiplying by 50. Now I'm probably not going to need to infer both of them, so why don't I finish reading the question now and then I'll see what I need. how many of the tickets sold were 240? So 3 times 50 is 150. And if you learn nothing else from this question, I hope you'll learn the following. Pause and infer. Pause and infer. Pause and infer. Pause and infer as you're reading the word problem. I probably would have spent close to 2 minutes just getting to the question mark. But at the question mark, I either have my answer or I realize the question is too hard for me. Either way, I'm picking something and moving on to the next one. So what's not likely to happen when I use this approach is I'm really unlikely to run out of time. I'm really unlikely to go over 2 minutes if I'm pausing and making inferences every step of the way. And I think there's also a much lower chance of making careless mistakes when I do the puzzles one at a time rather than dump 100 pieces on my desk and try to do 5 puzzles simultaneously. I think that's really maybe the biggest takeaway of the day, but I'd love to hear other thoughts and open this up a bit for conversation. If you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.